Hi everyone, I'm Roshni, and this summer I worked with Dr. Justin Riley and Dr. Abby Hutson, looking at how orographic features influence lake effect snowstorms. So a little bit about me first. I'm currently a rising senior at the University of California, Berkeley, studying environmental science and molecular environmental biology. I've also done research at Osaka University, where I modeled and assessed forest management scenarios. So first I want to give a little bit of background on how orographic features influence airflow, as well as what is lake effect storm. So what are orographic features? They're basically just terrain features that are related to hills or mountains, and this can include like dunes, plateaus, anything that kind of just rises out of the ground. And usually when an air mass encounters an orographic feature, it has two options. It could either do flow over, where it goes over the mountain, or does flow around, where it goes around the mountain. So flow over, which is also called an unblocked scenario, is basically when an air mass encounters an orographic feature and it rises up over the mountain. This is also called orographic lift, which then increases the relative humidity of the air parcel when it goes over the mountain. Orographic uplift creates precipitation higher on the terrain, which then leads to a high orographic ratio. And orographic ratio is just a fancy term to say that the ratio of the mountain precipitation is higher than the lowland precipitation. The other scenario is a block scenario or a flow around scenario. And that is when the air parcel doesn't have enough energy to go over the mountain. And so it kind of stays near the bottom of the terrain and has to go around the terrain instead. So when does flow over as opposed to flow around happen? It's because of three situations. One is when the barrier is thin or short. Two is when the cross barrier wind, which is just the wind that's going against the terrain, is strong. And the third one is when the flow is unstable, but we won't be getting into the third option. So lake effect snow, primarily for the Great Lakes region, is when cold northwesterly wind, usually coming from Canada or Alaska, blows over the warmer lake water. This allows the heat and moisture from the lake to transfer to the lower atmosphere. This then causes the air to rise, form clouds, and cause heavy snowfall downwind. And on the right, you can see a satellite image of the Great Lakes during a lake effect snowstorm. So the main requirement for lake effect snowstorms is a temperature difference between the atmosphere and the lake water, usually around 13 degrees Celsius. This typically happens in the winter months when that difference is really high, as you can see on this plot. And some important factors for lake effect snowstorms are fetch, which is just the amount of time the wind is crossing over the lake water, which then influences the amount of water vapor that is evaporated. Topography, which is what our project focuses on, which influences the airflow of the storm, as well as ice cover because it inhibits energy exchange with the air. Lake effect snowstorms have different patterns and they're called modes. The two main ones that we'll be looking at are long lake axis parallel storms, which are also considered a banded type of system, and a broad coverage, which is a non-banded system. They're named simply because of the shape of the storm. As you can see on the top left, that is a long lake axis parallel storm, which is very narrow and thin, versus on the right of that is the broad coverage, which is a lot broader. Oftentimes, nature is not perfect. Usually we get a hybrid of both, but we'll be focusing on those three mainly. There are other kinds too, but for this project, we won't be focusing on them. So let's get into the research. My project this summer was specifically a case study looking at the November 2022 Great Lakes lake effect snowstorm. I'm sure you guys have probably remembered that storm too. I wasn't here though. This happened during November 16th to November 20th, and our areas of focus for this project are the Buffalo area, which is east of Lake Erie, and Tug Hill Plateau, which is east of Lake Ontario. Both of these places received record amounts of snow. For example, Buffalo got 21.5 inches of snow on November 19th, and Tug Hill got 2 feet of snow during the storm. So the main research questions we're answering is, when a lake effect snowstorm encounters a terrain feature, does the flow get blocked or does the vertical motion get amplified by the terrain? And if so, how does the precipitation change based on that? Is the amount of precipitation change different, or is the distribution different? So our model data came using the Weather and Research Forecasting Model, or WARF for short. This is a mesoscale numerical weather prediction system created by UCAR. We modeled specifically from the 18th to the 20th in 15-minute intervals. And our model had a 3-kilometer grid spacing, which is run from here all the way to Briarwood Mall. And we had 2 runs. We had a 100% terrain run, which is the baseline run, as if like normal terrain conditions, what it is in like real life. And we also had a 0% terrain run, which is as if we took away all the terrain, it's all flat, there's nothing there, just to see what we can compare and see what actual storm features are happening because of the terrain. And we chose 4 cities for our analysis. We chose Silver Creek, Holland for Lake Erie sites, and Watertown and Worth Center for Lake Ontario sites. And as you can see, these cities were chosen based on the distribution of the terrain as well as the precipitation. And so Watertown and Silver Creek are the more lowland areas versus Worth Center and Holland are the higher terrain areas. So let's get into the results. So one thing you'll really notice in this time lapse of the storm is that on the 18th and 19th, it is a very long banded storm, as you can see from the shape. But on the 20th that you just saw, the wind shifted, which kind of pushed the storm into terrain and made it a bit broader. Because of that, we decided to focus on the storm in 2 different phases, the 18th and 19th, when there was a more long length axis parallel storm system, and then on the 20th, when things changed a bit. So this is the total precipitation that was accumulated on the 18th and 19th for the 100% terrain scenario. So normal conditions, normal terrain. And this is what it looked like for the 0% terrain scenario. So when I go back and forth, there's 2 things you can notice. One is that in the terrain scenario, the storm band is a bit shifted northward. And the second thing is that you can see is that the precipitation is a lot more intense at the axis. These 2 features are pretty clear indicators that this is a block system, but this actually doesn't really align with the literature. Goen et al. 2022 actually said that 500 meters of terrain height is actually not enough to block long lake axis parallel storms. So what could it be? What's really interesting, it turns out, is that the location of the terrain relative to the wind is really important. In Goen et al.'s paper, they were looking at terrain that was specifically downwind of the storm, versus when you look at our system, you see that the terrain is actually adjacent to the wind that's going north-south, southwesterly. This means that in Goen et al.'s paper, their cross-barrier wind, which is another important factor to see whether it's flow over or flow around scenarios, was really strong. It was the main flow of this of the system. Versus for us, the cross-barrier wind is actually not the main flow. It's actually kind of to the side of it, and instead the flow is going along the terrain. This means that our cross-barrier wind is a lot weaker than Goen et al.'s paper would suggest. And this can be verified when we look at vertical cross sections of the storm. This is on for Silver Creek and Holland, and as you can see, the contours, which are kind of around here, are rather weak, and that means that just the cross-barrier wind is really weak too. Also verified by when we look at Watertown's cross section, and actually what you can see here, this is a stronger case for a block system because there's the terrain here, and there's a little valley where Watertown is, and you can see the wind contours actually get a lot stronger here, which indicates that the flow is getting pushed into the valley where there is lower terrain. And additionally, on top of that, we can see there's a bit of deflection that is happening near the terrain. As you can see, the wind is kind of going this way instead of going along the terrain. But you might say, hey, Roshni, that's also happening in the no terrain scenario. So what's going on? So it turns out a property of long lake axis parallel storms is that there's this thing called land breeze convergence. And that basically means when the storm is, the air is rising within the storm, there's a vacuum on the bottom and needs to get all the air from our surroundings to fill in that gap. So all storms will have some slight deflection towards the axis. But what's really important to note is that in the terrain scenario, the deflection's a lot stronger. And that is a clear indicator that it is land breeze convergence added with the blocking from the terrain itself. And what does that mean for orographic ratio and precipitation distribution? As you can see here, both Silver Creek and Holland both have similar precipitation distributions and low orographic ratios. And that luckily aligns with our literature for what a block scenario would create and also for long lake axis parallels as per Beals et al. 2018. So let's go into the 20th, which is when our wind shifted. So this is the 100% terrain scenario for the 20th, as well as the 0 terrain scenario for the 20th as well. And one thing you can clearly see is from the 18th and 19th, the storm is a lot broader. So is it still long lake axis parallel? Is it something different? We can check at the data to see. So when we look at specifically Lake Erie, we see that the lowland and highland precipitation distributions are pretty similar, which would then indicate it is still long lake axis parallel storms. And when we cross-verify that with the shape of the storm, we're like, yeah, that is pretty still banded long lake axis. So that means that we can arrive to the same conclusions that we did for the 18th and 19th, for the 20th for these cities as well. But when we look at Lake Ontario cities, we see something very different. The orographic ratio in the terrain run is actually higher than the orographic ratio for the no terrain run, which doesn't really align with what a long lake axis parallel storm would do. So what could it be? When we look at the shape of the system, once again, we see that it's still actually kind of still pretty banded right up here, which kind of contradicts what the plots we just saw before. But when we look like an hour before the wind shifted, we see that it is indeed quite a broad coverage storm and doesn't really have those like long lake axis parallel band lines. And so what this just means is that before the wind shifted, the storm for the Lake Ontario cities was a broad coverage storm. And when the wind shifted, it just pushed the wind into the terrain and created convergence lines there. So when we look at the orographic ratio of these cities, once again, knowing that it's a broad coverage storm, we also see that there is a higher orographic ratio. And that does align with our literature that high orographic ratio and broad coverage storms are something that will create those. And additionally, on top of that, something that's really interesting is that on the terrain, you can actually see there's a little bit of precipitation that's happening on Tug Hill Plateau itself. And that is actually an indicator of orographic lift, which would then indicate a flow over situation. So in conclusion, for this storm and for this region, we see that the mode of the terrain as well as the location of the terrain relative to the wind is really important. So for long lake axis parallel storms with adjacent terrain to the wind, we see that there's more of a flow around situation happening with lower orographic ratio. But then when we have a broad coverage storm with terrainward wind, we see a more of a flow over situation with higher orographic ratio. And this aligns with Campbell et al. 2016 and Beals et al. 2018. And this project can be used to improve our understandings of interactions between lake effect snow convection and mechanisms of orographic precipitation, which then would influence storm outcomes, which would help us with forecasting. Of course, there are future questions we can answer with this project. One is seeing maybe different terrain heights and seeing different orographic ratios, as well as seeing different locations, because we looked at specifically where there were intersections between the storm and the terrain. Another thing we can look at is, since this is a case study for the Great Lakes for the specific storm, we can maybe apply it and see if it works for other storms in other regions of the world. And lastly, Beals et al. Actually mentioned that along with lake effect snow modes, zonal wind speed as well as lake convective available potential energy are really important factors for lake effect snow too. And we can see the intersections of those and terrain as well. I'd just like to express my sincerest gratitude to those that supported me in my time at Ann Arbor and CIGLR, especially my mentors, Abby Hutson and Justin Riley, as well as the CIGLR admin, such as Margaret Throckmorton, Mary Ogdell, and all my summer fellows and interns. Thank you.
Thank you for that wonderful presentation, Roshni. Do we have some questions?
Good talk. And do you have this a case study?
Mm-hmm.
But for another year, another case, for example, they have similar feature, or?
That would definitely be like the next step. Our project definitely specifically focused on this specific storm, and just to see like what was the airflow doing when it was encountering terrain, and like how is that different from our no terrain run and stuff like that. So I would love if we had more time to look at different storms, because I was also thinking while I was doing this project, like, does this apply? Do my conclusions apply to other parts of the world and other storms, even in the Great Lakes? So that would definitely be a great like future study to do.
Thank you.
Okay, other questions?
Thanks. Yeah, so I guess this is more of a comment, less of a question, but your figures were all very impressive and looked,
Thank you.
and looked basically publication ready. So you should be proud of that.
Thank you. I spent a lot of blood, sweat, and tears into those, for sure.
Yeah, I agree. Looked very, very polished. Got time for more questions?
As a Californian, what was interesting to you about studying snow, and why did you want to do this project?
So a big reason like I even applied to this project is like I've lived in California for a lot of my life and went to school in California, and so like I definitely like want to study climate science, and that includes the world. So one big reason I really like this project is because it would be focused on a region I've never done before, and like I didn't even know what lake effect snow was before like this summer. Like had to read it, do all the literature, and be like, wow, this is really cool. And so just like doing something new, something I've never encountered, but seeing like huge impacts. Like Buffalo was under so much feet of snow, and like it, hurt people's lives and stuff. So I think just the importance of the work, and also just doing something that is not just relevant to me, but also just still important to other people, was definitely a pull for this project.
Hey Roshni, nice
Mhm.
work.
Thank
I'm just curious to understand, in your study, you've considered two runs,
Mhm.
0 and 100%, like low and extreme.
Mhm.
Is there any specific reason why you didn't consider anything in between?
I think we specifically chose like 100%, which is just like the normal train, and 0% as like a good just control comparison. I think if we added more, which we could do more in the future, it would have confused and complicated the situation, especially because like in the literature itself, 500 meters is actually not high enough to really influence the storm flow. So even just seeing that normal conditions 100% does, we can then further research, can look and be like, does 50% do something? Does 25% do something? And then really get the physics of the storm. But this project was really just to see, does it actually even do anything in general in the first place? Yeah.
Okay. Thank you.
Yeah, of course. Thank you.
Super brief comment. Thanks for a really good talk. Just to add on to that, 100%, you could also go 150, 200. You could go, I love like idealized experiments where we can just really play with the configuration and see what the sensitivities are. That would be a really interesting area. But yeah, thanks. Great talk.
No, you're really right. I'd also be really interested to do 200%. I mean, it has less of like a bearing in real life, I guess, because there is no real 200% in those areas. But I think just for the science and just understanding it, I think that'd be a great next step too.
Okay, seeing no more questions, we're going to transition. Our next speaker is virtual, so it might take me an extra minute to get them set. So thank you very much.
Thank you, guys.